This problem is about a hoop of mass. We want to find the moment of inertia of it. It's got a total mass of 10 kilograms, and the radius is big R, and that's going to be 10 meters. Now, we're going to assume that's an infinitely thin hoop. So even though it looks like it has some thickness, each piece here is really just supposed to be infinitely thin. It would have its own length, which could typically be called ds. ds would be just that tiny piece of length. So to use calculus on it, you want to section it off into infinitely thin little pieces, and then we'll just add them up by going all the way around the hoop. Now, if you look closely at this situation, you'll realize that the distance from center to any given piece is going to be r. That's something that all the pieces have in common. And so if we were to just quickly calculate the moment of inertia of this hoop, we could say that it would be the total mass of the hoop times r squared, and that would actually be the final answer for this. The reason being that all the mass for the hoop is located a distance r from center, so it would actually have the same exact formula as if it was just one mass, like a point mass on a string revolving around some center axis. Imagine you've got a point mass on a string revolving around a circular path like that. And if the point mass had 10 kilograms and the hoop had 10 kilograms, then they would have the same moment of inertia, is the idea. But we want to show that through calculus. So how would we do that? Well, you could say that you're going to add up all the r squared dm's. And so why would I use that? Well, because each little piece has a length ds, but it also has a mass dm. And each piece is a distance r from center as well. Now I'm going to distinguish between little r and big R. In this problem they're the same, but in future problems they're not. R would be sort of a variable of integration that could potentially change. In this problem it doesn't change. But big R stands for the overall radius of the overall shape. Like, that's the difference between the two. So with that in mind, we need to have some limits for our integral. Like, this is how we're going to find the total moment of inertia. And we're going to assume that that each little piece would have a di, which is a tiny contribution to the moment of inertia. And so just taking the formula I equals mr squared, if we take the differential of both sides, in this case we would get that di would be r squared dm. Like, that would be the relationship between di and dm. Alright, so we basically want to add up all the little di's, the little contributions, so we'll have this. But we need limits for our integration. And we want to say, like, what do we want to go from and to? And it's our choice. So one way we could do it is to say we'll go from, let's say, s equals 0 to s equals 2 pi r. Now, why would I use those limits? Because S could be the arc length, and this is a little piece of S. And then you want to go all the way around until you've gone the full circumference. And the circumference of the hoop, of course, would be given by 2 pi r. So that's one possible choice for the limits. So then what would you do next? Well, we always start with this formula for moment of inertia integrations. But we want to replace dm with something where the differential would match our limits. Well, how would we do that? Well, the relationship we have between dm and ds would be this. You'd use the linear mass density. We've used that in the past. Linear mass density is going to be given by the total mass of the hoop, m over L. The mass divided by the length of the object, but here that would basically be the mass over the circumference, because that's the length around your shape. It's curved. Since it's curved, you might put that it's m over s, where s represents the arc length. So then we would differentiate dm over ds. Rearrange it. dm equals lambda ds. Then take those results and put them in place of the dm in the integration. So you would get this and that's great because now the limit variable matches the differential variable. We want to pull out anything that's constant. So the lambda is just a constant that could come out, but even the r can come out. And we don't even have to use little r here. We could change it to big R, since all the pieces have the same radius. So that's why it's constant, So you bring that stuff out, lambda r, you do s equals 0 to s equals 2 pi r, and then ds. Yeah, it should be lambda r squared. We're left behind with just a 1, basically, because everything came out. Then we could even replace the lambda with what we know it to be up above. So the lambda could be m over 2 pi r, total mass of the object divided by the circumference of the object, and then put your r squared. After we anti-differentiate, you get s, and then go from 0 to 2 pi r. So you can see what happens here. You get this, and then that, and then all this cancels, see? That'd be the final result. So it's a lot of calculus just to get to a result that we already knew what it was, just based on reasoning it out. But it's an interesting one to do because it's an easy introduction to some of the more difficult ones, I guess. So another way to set it up would be to say that you want to go from a theta of 0 and then add up all the little contributions to the moment of inertia and come back to a theta of 2 pi. And so you'd be creating what's called a polar integral if you did it that way. you start with your idea that the total moment of inertia is the integral of r squared dm, but you'd make your limits based on theta instead of like s or x or y or anything like that. We'll go from theta of 0 to theta of 2 pi, so integrating around a circle. But we still have to come up with a substitution for dm. Alright, so each little piece has a mass dm, and each little piece would have an arc length ds, but we'd come up with a new formula for ds based on the arc length formula. S equals r theta being the arc length formula. And you differentiate both sides to find that ds can be replaced with r d theta. That's always true with like polar types of integrations like these. Alright, so we'll use that eventually, but we also want to relate the dm to everything. So we have the idea of the linear mass density once again. And that would be lambda equals m over, let's say, c, which is the whole circumference. And you could say that lambda equals dm over dc. But the idea is that ds, it is dc. Tiny change in the arc length is the same as a tiny change in the circumference. So if you have that, you could say that it's equal to dm over ds, and then rearrange to find that dm is lambda ds. So these are all about just kind of playing with the differentials, finding their relationships, and now we could take what we got here for ds, plug it in place of this, so that you have dm equals lambda times r d theta, and then you would take what you got here and plug it in place of dm in the integration. So it'll be I equals, we'll go from theta equals 0 to theta equals 2 pi r squared, and then lambda r d theta. Alright, once again, the r's will be constant for every little piece of mass here. So we can go ahead and pull those out of the integration, and the lambda could come out too. Lambda times r cubed, go from theta equals 0 to theta equals 2 pi, leaves behind nothing, just a 1 basically. So your theta is defined as mass over circumference. This becomes a theta after you integrate, and then we'll go from 0 to 2 pi. You get m over 2 pi times r squared times 2 pi. And once again, not surprisingly, the integration works itself out. And we find the formula for the hoop. One last way to do it, and I'm just trying to like set up the future ones that are the ones where you do need calculus. Like this one, you don't even need calculus, but the future ones you do. One more like simple way to do it would be to say like your moment of inertia will be integral of r squared dm, and each little piece is dm, and just by symmetry they're all going to be the same as we go around the shape. But the overall shape is big M. Okay, these are dm. So if you were to just say go from m equals 0 to m equals big M, that would actually be valid here. And so the r squared would be constant, so it would come out. You'd go from 0 to big M dm, and you'd get just this little m from 0 to big M. And that's the simplest, I guess, integration that you could do to show that it's mr squared. Alright, so anyways, to finally answer the problem, the mass was 10 kilograms. The r is 10 meters. So therefore, the moment of inertia of this hoop would be 10 kilograms times 10 meters squared. It looks like 1,000. And the units would be kilogram meters squared. Now we just want to compare that to what happens if the mass is not uniformly like distributed on a hoop like that. What if instead it's a disc? Alright, say we take those 10 kilograms and flatten them out. Yeah, we'll flatten out the 10 kilograms so that it makes a disc shape rather than a hollow hoop. And now we want to find the moment of inertia of this. And so it's interesting to compare, trying to apply a torque to these different objects. Because they're similar, but they're also different. And I guess you want to think about your experience from the past. If you were to apply a torque, like an equal torque to both of these objects, which one would be easier to get it spinning? So just imagine that. You put your hand on this one. Alright, now you're going to apply a force. And that force creates a torque. Why? Because it's a distance from the center, axis of revolution. Alright, we're going to try that on both of these. Apply the same force so it's the same torque. Now, the torque that you create would be a pseudo vector. And so according to the right-hand rule, what would that mean? It would mean that your R points one way, and the force points 90 degrees to that. The torque would be given by R cross F. So using the right-hand rule, you point your finger in the direction of R. It's the pointer finger I'm talking about. So this is your pointer. You point your middle in the direction of the force, because it's the second variable in the cross product. See, this one's got to be the pointer, and then the force is going to be the middle. What happens is the torque direction is given by the thumb. So we would have, some other fingers here. It would be like that, and then the thumb would point back in space. So there's the R. There's the force, which is the middle. And then the thumb points back in space. And that is the direction of what's called the pseudo vector of torque. And so the torque points that way, like back along the x-axis. No particle is actually pushed backwards into space like that, though. That's why it's called a pseudo vector. But what it tells you is that all the particles feel like they're being forced in a clockwise fashion. And it's the negative x. You know, the torque is in the negative x direction. So that's why we often say, like, clockwise torques are negative torques. Alright, but the same thing would happen with this shape down here. And we want to know which one is going to be easier to get it spinning. It's kind of an optical illusion because, like, the one down below looks like it's thicker, like it looks like it's more dense or something, like it looks like it has more mass to people. But they actually have the same mass. The mass of each is 10 kilograms. Yeah, so even though they look like, one would be heavier than the other, they're actually the same mass, is the idea. And we just want to guess which one has the higher moment of inertia. Because a higher moment of inertia means more resistance to angular acceleration. But a lower moment of inertia means less resistance to angular acceleration. Alright, let's try to integrate it. So with this, we typically want to imagine just a section of the disk that is a hoop. Alright, because you always want to draw like a typical piece that you can use to add up to get the whole shape. So what I'm talking about is concentric hoops here that we could integrate from the inside out to the edge. Alright, now the overall shape has a radius of big R, which is 10 meters, and it has a mass, an overall mass of 10 kilograms. But each of these shapes, these hoops here, could be thought of as having an infinitely thin area dA. Alright, now what would the thickness of the hoop be? I'm talking about, like, what would this thickness be from the inside of the hoop to the outside? It's infinitely thin. And so that would actually be dr. Okay, why? Because the radius goes from center to the outside, and if we were to set up limits for our integral, it would be good to go from a little r of 0 to a little r of big R. What does that mean? It means you're going from the center, where r equals 0, because you haven't gone anywhere yet, and then you go out to the edge, r equals big R. So those would be good limits to have. So that's dr. Now what's the length around that little hoop? It wouldn't be infinitely small. It would have a substantial circumference. And you could just call it c. But keep in mind that C is not going to be the same for all the hoops. Like, for example, a hoop that's out here at the edge, if we were to add up the very last area, that hoop would have a much larger circumference than the one on the inside. So C is going to be a function of R, and that's important to do in this integration. Now we could come up with a formula for C. It would just be that C of R is going to be 2 pi R. You'd use the circumference formula for a circle. Alright, but either way, we want to start off with the typical moment of inertia type of calculation, which would be just an integral of r squared dm. But the whole trick is to get dm out and replace it, in this case, hopefully with a dr, some kind of function times dr. Alright, so what relationships would we have? Well, this time we're dealing with an area instead of a length. So we could use the area mass density, which could be called d or sometimes sigma. Alright, and sigma would be the total mass of the shape divided by the total area of the shape. But if we differentiate, you get this, dm over dA. So if we just rearrange that result, you find that dm is equal to sigma dA. So we're making progress, because this could go in place of the dm there. Okay, so we can work our way toward dr, is the idea. So you get r squared sigma dA. So it's better, but we still have more substitutions to do. So what's the formula for dA then? All the areas are not going to be the same. See, the one on the outside here, it's going to have more area than one on the inside. So the formula could be found by multiplying a circumference times a width. So C of R is our circumference formula, which depends on R, and then dr is our width, which is actually going to be the same for all the hoops. Alright, so we'd have that dA is going to be 2 pi r dr. And you'd take that result and put it in place of dA in the integral. And now we have what we need. We wanted a differential which matched the limits of integration. Now we have that. Alright, so one difference between this integral and the previous is that little r is changing all the time. It's not constant this time for all hoops. So we can't take it out of the integration this time. But there are certain things we can take out, like the sigma and the 2 pi. So let's take those out. And then we would go from 0 to r of r cubed, it looks like, dr. Now sigma can be replaced with its formula based on the mass of the object and the overall area of the object. So we'd get m, and we want a formula for that area. We could just do that, but we want to replace it with pi r squared. So you get I equals m over pi. We'll use big R because we're talking about the overall area of the shape, which we don't need to use little r. We just use big R for that. And you have this. Okay, we'll take the antiderivative of r cubed, which would be r to the 4th over 4. We'll go from 0 to r. Now we'll plug in the r to get this. And then we just want to try and simplify it and see what comes out. Alright, so the pi's cancel. Some of the r's will cancel. And the 2 and the 4 can cancel. So what do you get? 1/2 mr squared. Which is a different result than we got with the other integration. So what that means is that this disk will have half the moment of inertia that a hoop of the same mass had. So to finally answer the question of which one is easier to angularly accelerate, like which one can you get spinning more easily, this one is easier to angularly accelerate. And this one is more difficult to angularly accelerate. Okay, so this one has the higher moment of inertia, even though it has the same mass as the other one. It has the lower moment of inertia. And then how can we explain that just intuitively? Well, the idea is that all the mass is concentrated far away from the axis of rotation, which means that the mass has a larger path to travel because it's farther away. In this example, the mass is located all throughout the shape. And so some of the particles would be really far away from center, but others are really close. And some of them are like right at center, and they don't take any effort to get them angularly accelerating at all. Like they would just kind of spin with no problem. And if you average it out according to calculus, it turns out that the I of the disk is going to be 1/2 the I of the hoop. Alright, now why does the I matter? Because of Newton's second law for rotation, which says that the net torque equals I times alpha. So the idea being that for the disk, I goes down, but you're applying the same net torque to both. And so that means that the angular acceleration goes up for the disk, making it easier to spin.